Hello everyone! Today we are going to continue our lesson. Our last part is about prisms and dispersion. Dispersion, what is it? It's when the light separates into its components. So it's the process of separating polychromatic light into its component wavelength. What's the meaning of polychromatic light? It is the white light. Why it's called like polychromatic light? Because it's made of many monochromatic lights, so that's why it's called polychromatic. So it's the one that has many wavelengths, it's not made of a single wavelength. Okay, we will talk about prism. You all know prism. The prism is a very important one because we use it in physics to prove that the white light is made of many colors. The prism has many shapes, but the one that we are familiar with, it's the triangular prism, right? The one that has like 3 surfaces. Okay, so it's made of a glass and it has many plane surfaces with an angle with each other. When we shine white light on the prism, we can notice that from the opposite side, from the other side, we see different colors. Why? Because as we learned in this chapter, when light passes from a medium, like here from air to another medium to glass, it changes speed. We said when the light enters glass, its speed decreases because the glass is a more dense material than the air. So the light is going to slow down. And when the light slows down, how does it bend? Does it bend toward the normal or away from the normal? It bends toward the normal, right? Okay, so this is the point at which the incident ray hits the surface. Here, if you want to draw the normal, you can draw it for sure how? Perpendicularly at this point. Okay, so this is, girls, the original path of light. This is the original path of light. The light will not continue like this in glass. It will slow down. So when it slows down, it bends toward the normal. This is the normal N and not away from the normal. Okay? So you show first the original path of light, then you ask yourself, how will it bend, toward or away? Since it slows down, so it will bend toward. Okay, now girls, we will see that different colors bend at different angles. Why these colors, they do not bend all of them at the same angle? If they bend at the same angle, we will not recognize them as colors because they will join to give us white, right? Okay, so why they bend at different angles? Here we have to go back to the equation, which is very easy. Speed of light is equal to wavelength times frequency. Okay, when you learned about light, okay, we said in the same medium such as air, okay, in the air, all the light, they have the same speed. Radio waves, gamma rays, all the light, visible light, even invisible light, red, yellow, orange, all of them, they have the same speed. Why? Because when wavelength increases, frequency decreases in order to what? To maintain the same speed in the same medium, okay? But when light enters another medium, such as here glass, what happens? The wave frequency stays the same, doesn't change, and wavelength, what? It changes. When white light here enters glass, so I have different colors. Each color, it has what? A specific wavelength, and they have all the same frequency. Why? If you remember, girls, when we talked about the wavefront model, if wavefronts are moving from air to water, you can recheck this paragraph, okay? We said that the number of wavefronts in water will not increase or decrease. The same number of wavefronts will stay, okay? But the wavefronts, they will become closer to each other when they enter water, for sure, because light slows down in water. So wavefronts get closer to each other and they turn how? They turn toward the normal because the light slows down. Okay, so that's why I explained for you before, that the frequency doesn't change, the number of wavefronts produced per second will not change, but the wavelength changes. Okay, now for the red, you know, the visible light is made of Roy GBIV, GBIV. Okay, and if you remember, red has the longest wavelength, and violet has what? The shortest wavelength, the shortest one. Okay, so red has the longest wavelength. So inside the glass, which one is the fastest among the colors? I'm just comparing between the colors. So red is the fastest among the colors, and violet, because the violet, it has what? The shortest wavelength. So shortest wavelength gives us what? The lowest speed in this substance. Okay, so in a glass prism, violet has the lowest speed. It is the slowest. What means slowest? So it will bend toward the normal the most. See? It is the one which is closest to the normal. More than indigo, more than blue, more than green, more than yellow, more than orange, more than red. Because in this substance, violet is the slowest. So it is the one that it will bend the most. And red, it will bend the least. So that's why each color bends at a specific angle. So that's why they separate. We recognize them as colors. And even girls, when they exit the prism, the same thing. So the red continues. See, this is now the point at which this red light hits the backside. So you draw here the normal. Sorry, it's like the normal should be perpendicular to this point, so it is like this. Okay, and it bends away from the normal here. Why? Because this is the original path of light. It bends away from the normal, not towards it. Why? Because it's entering air, which is less dense. It will speed up. Okay, and the same for each color, and we get what? All the colors here. So this is the process how the prism separate colors. So a prism, why the prism can separate colors? Because the speed of light traveling through a medium depends on wavelength. This is the key. This is the reason behind the separation of colors, because the speed depends on wavelength here, not the frequency. Frequency is constant, we don't talk about it usually. Okay, so the one that has the longest wavelength is the red, the one that has the lowest wavelength is the violet. So violet lowest wavelength, so the slowest, so bends the most, red bends the least. Let's read the explanation together. So light waves have all the same speed where? In vacuum. But when light wave enter a medium, the speed of this light now depends on what? Depends on the wavelength. Okay? When the wavelength is long, the speed is high. When the wavelength is short, the speed is low. In a specific medium, like water, glass, okay? A white light has all the colors in order of longest, which is red, okay, to shortest, which is violet. The violet has the shortest and red has the longest, so violet travels slower than red, so it's obvious the violet will bend more than the red because it's slower than red. So violet bends more than red, and as it passes from prism also to the air. When white light enters a prism, the light exiting the prism is separated into colors, and violet bends the most, this is the result, and the red bends the least. Okay. Now we will talk about rainbows, which has a very similar concept to the dispersion. Okay, pay attention with me how rainbows form. We know, girls, that rainbow can only be seen when the rain and the sun occur at the same time. Okay, why? So because the sunlight enters the water droplets. Let's see what happens when light coming from sun enters a water droplet. Light is moving from air to water, so what will it do? It will refract. Okay, it will bend. How? Toward or away? Since it's entering our medium which is more dense than the first, so it will bend toward, it will slow down. Okay, and the same thing, because here the speed of light depends on wavelength, and red has the longest wavelength and violet the lowest. Here they show you like blue before the violet. Okay, so violet is the slowest, so it bends the most, and red bends the least. And as they hit the backside of the droplet, here total internal reflection occurs. Why? Because, girls, when they hit the backside, they hit it with an angle of incidence theta I bigger than critical angle. Okay, so they reflect back to the front side. When they reflect back to the front side, they will exit the droplet. They will not stay inside it. So they will exit the droplet, the same thing, from water to air now. See, here, this is the point at which the red hits the droplet, and this is the point at which the blue hits the droplet. This is the normal for red, and this is the normal for blue. Okay, see, girls, this is the original path of red. Will it continue like this? No, it will bend. How? It will speed up. It will bend away from the normal, not towards. See, this is the normal. The same for blue. This is the original path of a blue. Okay, since it speed up, when it enters air, it will bend away. Okay, so girls, here we get also different colors in order from red to violet, and this is how we see the rainbow. Okay, in order from red to violet. So rainbows are a result of dispersion of colors, which is caused by refraction. Refraction results from the change in speed of light as it passes from medium to another. This is the definition of refraction. Okay, so here again, sunlight is refracted. You will see here, it will refract as it enters the raindrop, which causes different colors. Different colors means different wavelength to separate. Okay, red bends the least, violet bends the most. These when they reflect, these reflected rays, they will exit the droplet, and also violet bends the most and red bends the least. And girls, here the violet always will leave the droplet by making an angle of 40 degrees with the incoming light. This is the incoming light. Okay, see, now the violet is going to leave. Okay, the violet is going to leave and the red is going to leave at the same time. The angle here between the violet and the incoming light is 40. Okay, and the angle between red and the sunlight is 42. So only 2 degrees is the difference between violet and red as they leave the droplet. Okay, but for sure, like for far distances, we think that it's more. Okay, so this is the angle here between them. It's just 2. So again, here the angle between the violet and the incoming light is 40 degrees, and the angle between the red and the incoming light is 42. How they found them? For sure, okay, based on the study of this refraction and the drawings. Okay, now Girls, we usually see our rainbow like this, right? Okay, so each droplet is doing the same thing, as I explained before. Each droplet does the same. But why here, when I have red, I see only red? Why here it's only red? Why here it's only, for example, yellow? Why here it's only green? And why here it's only violet? What happens is, like for the droplet that is here at high elevation, let's take this one, the one which is circled here, okay? This, see, the droplet here is giving rays red and violet. Focus on these, please. Red and violet. For an observer standing here, he will get the red light, but the violet light will pass over the observer, so the observer will not get it. So that's why the observer here sees this point as only what? Red. As only red. Okay? A droplet below, let's say that I have another droplet below here at lower elevation. This droplet is doing the same thing, is for sure giving all the colors, okay, refracting all the colors. Okay, so at lower elevation the red light will be like directed toward the ground, so we will not get it, but what, the violet light will enter our eyes, so we see this arc as what, or this place as violet. Okay, and the same thing happens between these droplets at all elevations. So when the observer views a raindrop high in the sky, such as this one, raindrop number 1, okay, the red light reaches the eyes, but the violet is what? It bends more than the red, right? So it's above it. It's above it. So it doesn't enter the eyes. It passes over the observer. Hence, the observer sees this droplet as only red. Okay, similarly, a drop which is lower in sky would direct violet light toward the observer and appear to be violet. So this droplet is going to appear to be violet only, and for sure it gives also red, but the red here is directed toward the ground, so that's why we just see it as violet. Okay?
Did you know that a rainbow is actually a full circle? But since we see it on the ground, we generally see it as a semicircle. Rainbows can be seen not just in rain, but also in mist, spray, fog, and dew. So now whenever it's raining, look out for the sun. Who knows, you might just spot a rainbow.
Okay, and this is the other one. It's about what I explained just now.
Down here, this water droplet will only send red light to your eyes, and the violet light will pass above you. It's the droplets down here that send violet light to you, and the violet light will appear to be coming from lower in the sky, as it does.
Okay. Let's continue. So you have this video also if you want to know more about rainbows. Now, the last part in our lesson is about lens aberrations. You heard about this word aberration in mirrors, if you remember, when we talked about spherical aberration. I will remind you about its concept. We said spherical aberration occurs when the rays coming, okay, they do not all meet at the specific point, which is the focal point, rays coming from a very far or distant object. So here with lenses, we have the same phenomenon. We have spherical aberration, so spherical aberration also occurs for lenses, not only for mirrors. Why? Because if we have parallel rays, for example, coming from star, the rays that are near to the axis, this one and this one, the ones that are near to the axis, that we call them paraxial rays, they meet at a specific point, here, the focal point, but the rays that are far from the principal axis, or we can say that the rays that are near the ends of the lens, they meet at a focal point which is closer. See, this one is closer to the lens than this one. Okay, so here the image as a result will not be that clear, it will be blurred, right? Okay, so this is the first type of aberration that happens with lenses. Spherical aberrations occur for lenses also. It results from the fact that the focal points of light rays from the principal axis far from the principal axis are different from the focal points of the rays that are near to the principal axis. Okay, so the paraxial rays, they meet at a point different than the point or different than the focal point of the rays that are far from the principal axis. This is the first type of aberration that occurs with lenses. Unfortunately, here we have another type of aberration for lenses, which is called chromatic aberration. Chromatic aberration is the focusing of different colors of light at different distances behind the lens. Girls, here, since the light is passing through lens, not like the mirror, the light is just bouncing off the surface of the mirror. That's why for mirrors we didn't talk about this aberration, chromatic aberration. But here for lens, the light is passing through it, okay? And when the light passes through it, as we said for dispersion, the red light bends the least and the violet bends the most, right? Okay, so here we have like separation of colors. We didn't mention it before because it's not that big separation of colors, okay? In our work we usually consider it as one line, okay? But in reality it's not. So in reality the red is separated from violet because red bends the least and violet bends the most. So here the red lights are going to meet at a specific point called the focal point R, FR, and the violet rays are going to meet also at a specific point which is called focal point violet, FV. And for the other colors, their focal points is in between them, okay? So here we have another type of aberration for lenses, which is chromatic aberration. In order to fix this chromatic aberration, what can we do? We can use a diverging lens. Why? Because diverging lens, it makes the opposite as converging. So when we use these two together as shown here, with one converging and the other diverging, like this, we fix the passage of colors and we make them all intersect at one point. So because a diverging lens has the opposite shape, so chromatic aberration for diverging lens is opposite that for the one of converging. So chromatic aberration can be greatly reduced by the use of combination of converging and diverging lenses made of two different types of glasses.